Welcome to the Introduction to Compressed Air module of the IMI Precision Engineering training program. In this module, we will be learning about what compressed air is and how we use it. You'll hear some of the common terms we use and understand the basics behind a compressed air system in an industrial context. Let's start with the basics. What is compressed air? It's moving the air that's all around us into a vessel and compressing it. Once compressed, we have a potential energy source. One of the simplest forms of air compressor is a bicycle pump. As we pull the handle back, we draw air into the chamber. As we push the handle, we compress it. This is the principle that most compressors work on, with a motor replacing your arm and a receiver to store the compressed air or energy. There are a number of benefits of using compressed air over other forms of energy. Some of the biggest factors include: compressed air energy is clean. Leaking air doesn't pollute the environment in which it sits as a hydraulic system would. Oil being sprayed at high pressure means a big cleanup and has cost implications, securing drains, etc. It doesn't arc and can work in different pressures and temperatures and weather conditions. Most facilities have a compressed air capability, which is installed along with other utilities at the time of construction. Compressed air can be controlled in two ways: pressure and flow, and if it's done correctly, without affecting one another. Once the ring main has been installed, the relative cost of peripheral components is low, especially when compared to hydraulic and electric alternatives. Hydraulic systems need to be closed, with pipes returning to where they started. Overall, the cost can be 3 times that of a pneumatic system. Electrical systems can be even more complex, sometimes costing 10 times that of a pneumatic system. Remember to treat it with respect though. Even at 2 bar or 30 psi, it can break skin and cause an embolism. Introducing pressure. The more pressure a system has, the more energy it has. Increasing the pressure increases the amount of energy the system has and the force it can exert. For example, a cylinder that cuts a 2 mm piece of aluminium would need more pressure to cut a thicker piece of aluminium. The SI, or International System of Units for pressure, is the bar. Another common unit, sometimes referred to as an imperial unit that is used, is the PSI, or pounds per square inch. Introducing flow. Flow is the amount of air that can flow over a given time. Increasing flow increases the speed an actuator operates at. The SI, or International System of Units for flow, is decimeter cubed per second. However, we often see other units, typically liters per minute. It's useful to know that a decimeter cubed is equal to a liter. To convert decimeter cubed per second to liters per minute, we just multiply by 60. In America, we use SCFM, standard cubic feet per minute, with 1 liter per second equals 2.12 SCFM. Most of the things around you exist in part thanks to compressed air, from inflating tires to medical applications, from air suspension to fairground rides, from warehouses to assembly lines. It's important to remember that the examples you are about to see represent best practice and aren't always reflected on client sites. This background knowledge may allow you to help a customer who is having problems with their system and spot dangerous situations. Let's have a look at how compressed air is generated. Here is a typical setup, although in reality, the compressor is usually sited in its own compressor house to isolate the noise and heat. In some systems, there may also be a dryer fitted just after the compressor. The compressor will collect air from the local environment. It might be damp or dirty, caused by high humidity or passing cars, for example. The process of compression creates heat as air molecules collide more frequently. The air receiver is where the compressed air is stored. Think of it as a battery. It's where the energy is stored. The safety valve will release air if the pressure rises above the set pressure, for example, 10 bar. The pressure gauge displays the pressure inside the tank. It's advisable to locate the air receiver in the coolest place possible without dropping below freezing. Cool air holds less water and is denser. In the receiver, the water condenses and drops to the bottom of the tank, and so less air is stored in this space. The amount of water in the air will depend on many variables, including geography, seasons, and temperature. The condensate drain allows that water to drain away. It may be a legal requirement in your country to dispose of this correctly, as it could contain oil and other contaminants. The drain valve allows this drain to be switched on and off. The isolating valve allows the supply of air to be disconnected from the ring main. The distribution pipe allows all the energy stored in the air to circulate through the system. Now let's look at some of the terms used here and in other parts of the compressed air world. Upstream refers to anything in a compressed air system before the point you are dealing with. Downstream is after. You can see from this example, the air receiver is upstream of the isolating valve and the distribution pipe is downstream. You may have heard the term ring main before. It's sometimes associated with a circuit in your home. We use the same term with compressed air. A ring main is used to evenly distribute compressed air. If a ring main wasn't used and the air was supplied in one long line, the air pressure would get lower at each point in the system. A factory may have one ring main serving the entire facility, or it may split the supply into areas or zones. Each zone would have its own ring main, allowing the air supply to be isolated when not needed. There are 4 valves in this visualization. They are located in such a way to isolate half of the ring main, allowing maintenance or repair while the other half continues operation. It's important to exhaust air in the isolated part of the system before carrying out any maintenance. The ring main will slope to the corner, allowing any water that forms should the temperature drop to flow toward the drains. IMI Norgren supply dead leg drains. These valves are below each corner and allow the fluid to be drained, and a shut-off valve should be included above them to allow for servicing. Fluid may be contaminated, so it should be disposed of correctly. The take-off points are where air is taken from the ring main to a point of use, typically a pneumatic tool, machine, or bench. Notice the swan neck that comes from the top of the ring main. Taking air from the top will inhibit any fluid entering the downpipe, and the swan neck provides the smoothest route for the air. Hard angles or elbows will slow airflow. Many IMI Norgren products are found at the end of these downpipes, at the point of use. Notice the air prep unit, which includes a shut-off valve. The colors in the illustration refer to different sections, which are all part of the same system IMI Norgren has used for the last 15 years. That brings us to the end of this module. Remember, the theory behind these products has stayed the same for decades. For example, a general-purpose filter is still a general-purpose filter, although the designs and materials may have been improved over the years. So, a basic grasp of what these products are and how they work is crucial, and will provide a background knowledge that will serve you well every day. You should now have an understanding of the basics behind compressed air, including why we use it, the advantages and limitations, and the basic setup in an industrial context. These learning points are the perfect grounding for the rest of the modules in the suite. Please visit the site to find out more.